Hi everyone. Today we are talking about the calculus component of solving for a moment of inertia. So before we talked about how to find the moment of inertia for a system of particles, now we're going to talk about continuous objects. So first, let's discuss why is calculus necessary here. So if we look at the equation that moment of inertia is the summation of all particles times the square of their radius, we run into the issue that there could be a potentially infinite number of particles in this continuous object. Obviously, it's not infinite, but the math would really make it seem like we're just traveling on and on to infinity, because we would have to find the mass. Oh, if it's the same density or the same material, then the mass would be the same, but the radii would be changing at such a small magnitude that you would be doing that summation forever. Right? Now the question is derivatives or integrals. So we are going to do an integral here. Integrals are really important in calculus when you want to analyze across some variable, like across a distance, across time. Here we're going to analyze across a length. We can also analyze across a radius, across an entire volume. When you want to analyze across a variable, you use an integral. So that's what we're going to use. Now, how many variables can we do this? Can we have, how many variables can we have to do this calculus? So we want one, right? So when we did our integral of r squared dm, right, for our other lessons, we wanted to find something that resolved the dm issue, right? So we want this in terms of dr so that we can actually integrate the r squared. So this is what we're going to try and narrow this down to, right? So we'll start with the integral of r squared dm. But what we're going to do is work our way towards an integral with respect to radius, dr. So let's look at this rod over here. Okay, we have a rod of uniform linear density being rotated about point O. Okay, you can see O is, we're going to assume it is the center of mass. Okay. So if we start with I equals the integral of r squared dm, okay, first we want to talk about the various densities. Okay, so we start with lambda. Lambda is linear density. This can be shown as dm over dr or dm over dl. Okay, this can also just equal mass divided by length, right? Then you have sigma. This is dm over dA. And then you have rho, which is dm over dv, right? So lambda is the one that can kind of, the denominator can get kind of fluid. You can use any kind of distance in there depending on what object you're dealing with, right? It could be with respect to the radius of a linear object, the length of a linear object. So that can actually change a little bit. But with sigma, that's got to be area, and with rho, it's got to be volume. So lambda is the only one with any kind of fluidity or any kind of varying components there. Now we're going to use linear because we're dealing with just a linear rod, okay, linear uniform density. So we're not going to assume this is a three-dimensional object or assume that this is some long cylinder. We're just assuming it is a one-dimensional rod, kind of. So we will start by substituting dm, right? Using this equation, dm equals lambda dr. So we will say that the integral of r squared lambda dr is our next step, right? Now we also need bounds. These integrals don't give a value if you don't have a bound. It will just give you an approximate function to find your answer. So let's give it bounds. If our axis of rotation, okay, right here, this is going to be our 0 point, then we're going to start over here and work our way here. Okay. So we'll call this negative L over 2 and L over 2. Okay, L over 2 meaning radius, right? We want to keep it in terms of length. because that is the variable that we were given. So this is negative L over 2 to L over 2, right? Now we're just going to evaluate this integral. I'm going to take that lambda out while we do this integral, so we'll get r cubed over 3 from negative L over 2 to L over 2. Now expanding this is going to get complicated because we'll have fractions that are going to be cubed and everything. So this will be lambda times L over 2 cubed divided by 3 minus negative L over 2 cubed divided by 3. Now, when we evaluate these cubes, remember that if there's an odd exponent, you keep a negative sign. Only even exponents actually eliminate a negative and make it positive. So we will have lambda times L cubed over 8 over 3 plus L cubed over 8 over 3. Now I'll work this out algebraically. That's going to be L cubed over 24 plus another L cubed over 24. And then you will arrive at lambda L cubed over 12, right? Because you're going to have 2 over 24. That'll give you 12. Now let's eliminate that lambda. Lambda is just going to muddy the water there. So we will substitute m over L for lambda. So zoom back in. We've got m over L times L cubed over 12. That's going to cancel one of those guys. And now we've got ml squared over 12. Okay. So that is the moment of inertia of a uniformly dense rod rotating about its center of mass. Okay. And that's how we're able to do this with calculus. Now, let's talk about 3D solid and uniformly dense objects. First, we're going to look at this picture on the right and answer this question. Which of the following varies if we were to cut thinly sliced cylindrical shells of radius r, thickness dr, and length L? So as we cut shells through this cylinder, we're going to have to make either start at the center and go outward, bigger and bigger and bigger, or start at the outside and go smaller, 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 right? So as we cut these thinly sliced cylindrical shells, what we're doing here is we're kind of imagining integrating, right? To integrate, you kind of imagine that you are making these small segmented pieces and you're going to kind of sum that up, right? So as we go, is the radius going to vary or is it going to stay constant? Well, that will vary, okay? Every time you make a new shell, you're out of material. So you have to go either smaller or go larger to change that radius, right? The height of the cylinders. We're not changing the height any, right? So that will be constant. That will not vary. The height of the cylinders are fine. The volume. Now the volume is going to change, right? As you get a larger radius, you now have more material, and that more material is going to lead to more volume. So that is not constant. That's going to vary with every shell. But the density, it is already said that it is uniformly dense, and if we are keeping the same material for every shell, then the density will remain constant. Okay? Now here's the trick. Which variable do we want to integrate? Well, we want to integrate with respect to radius, right? We want dr, right? So if we want to integrate with respect to dr, let's show how we integrate the moment of inertia for this cylinder. Now we're not doing cylindrical shells, we're doing the cylinder. Now, we will start with I equals the integral of r squared dm. That is the definition of moment of inertia. We don't start with anything different. Now, let's break down dm. Okay, this is a 3D object, so we are going to use rho, which is dm divided by dv, or just mass divided by volume, right? Now, if we want to substitute dm out, right, dm could be rho dv. However, we don't want dv, we want dr. So let's get volume in terms of radius, just like how we got mass in terms of volume. So V, okay, the volume of a cylinder is pi r squared h, okay, the height of the cylinder. So if we do dv, we're going to differentiate. We're going to take the derivative with respect to the radius. So the radius is r squared. That will become 2r. So you've got 2 pi rh dr, symbolizing that we took the derivative. Right? So now we've got dm in terms of dv, and then we've got dv in terms of dr. So we will substitute all of this as rho. Actually, you know what? I'm going to keep that all the constants out first. 2 pi rho h r dr. Right? And we will substitute that in for our dm. So now we have the integral of 2 pi rho h, and now that r times r squared becomes r cubed dr. Now, there are two ways to do this problem, and I'll see if I can get through both of them in a timely manner. You can either substitute for density early on, or you can do it after you do your integral. I'll do it the way I would naturally do it, is after the integral, but you can do it before the integral as well. So our bounds will be from 0 to radius r, right? Our starting point, our starting point over here will be the center of mass right there, and then we're going to go all the way out to the large radius r, right? So since we're differentiating in 3 dimensions, you start in the middle, and you will go all the way out until you hit the full radius of the cylinder. So let's see what we do first. I get everything that's not being integrated out. So this would be 2 pi rho h times the integral of 0 to r of r cubed dr. Right? How much room do I have? I got room. So we've got 2 pi rho h times r to the 4th over 4 from 0 to r. Your initial value is 0, so you can just plug in your final value. You then have 2 pi rho h times r to the 4th over 4. Okay. However, that's too messy, and that's not an acceptable answer. So let's go back and start simplifying. Now, this is where I said you can substitute rho, okay, that density. Density being mass times mass divided by volume, that could be mass divided by pi r squared h. Okay? Now, the density, that radius is going to be the capital R. It's not lowercase because the radius for the density of the object is determined by the entire radius. The small r shows a changing radius. Capital R is your final total radius of the object. So we will substitute this guy for rho. So we've got 2 pi h times m divided by pi r squared h times r to the 4th over 4. Okay? So now we can cancel things out. Pi goes away, h goes away, 2 of those r's go away, and that 2 over 4 becomes 1/2. So we will end with mass times radius squared divided by 2. And that's how you can solve that. Now, I will show you the other way real quick. I'm going to take this guy and bring him down here. Okay? So we've got the integral from 0 to r of 2 pi rho h r cubed dr. Okay? Again, I recommend you pull all of that stuff out. So then we have 2 pi h times m over pi r squared h times the integral from 0 to r of r cubed dr. Now, again, you have got to use the capital R on your density. If you use the lowercase r, that implies that it's going to change and it can't come out of the integral. But it's not going to change. The density is set for that object. All right, now let's get back to this. We've got pi gone, h is gone, and so we are left with a different looking integral. Okay, now we've got 2m divided by r squared, and now we evaluate the integral. That's going to be r to the 4th over 4. Now 2/4 becomes 1/2, and those two r's go away to give you mr squared over 2. Okay. So you'll get the same answer. I prefer to do it the first method because I do my calculus techniques first, and then I do my algebra. When I do this, I feel like this shifts to my algebra brain, then my calculus brain, then back to my algebra brain, and it just doesn't work for my brain. But remember, you got to do math how your brain works. Don't try and force a method that's going to give you the wrong answer because it's going to confuse you. So you do you, but there are those two methods to do that. All right, now our last discussion is over prefab moments of inertia. We call them prefabs because they're previously fabricated, right? They were already made because their integrals are relatively easy, but these are very common objects that are going to be rotated in our problems. So you can look through all of these. We will be using these moments of inertia. We'll call them prefabs throughout this chapter and through the remaining chapters in the class if we've got rotating objects. So we'll refer to these often. These are also readily available online. Now, which ones have we already derived? Well, we derived that guy. We also did that one. And we just got finished doing that, mr squared over 2. Okay, so we've got solid cylinder or disk. We did the long thin rod with a rotational axis through the center. That was ml squared over 12. Then we did it through the end, ml squared over 3. So we've already done 3 of these, actually, not just 2. Now, something to raise a question, right? If we have a solid object rotated about versus a shell of that object, which one would you assume is going to be the greater moment of inertia, right? However, we are going to say that these are equal in mass and radius / length, okay? I wouldn't use a slash. In mass, radius, and length. So, for example, we have a solid cylinder, mr squared over 2. Okay, this is for a cylinder. The solid is mr squared over 2. But if you look up, the shell is mr squared, which is double the solid. Now let's look at what if we have a sphere. If we have a sphere over here, solid, 2/5 mr squared, but then the shell over here is 2/3 mr squared. Okay? So if we're looking at two objects with equal mass and equal radius, which we are in this diagram, all of these m's are capital, all of the radii are capital. Only with the example of a hollow cylinder or the rectangular plate where you've got the little a and the little b is that going to change. Everything else is the same mass, same radius, or if there is an L involved, same length, right? So when you compare two objects of equal mass, the shell will have a greater moment of inertia. And why is that? Well, so when you think of a shell, you automatically think that you are taking the inside of the sphere and you're taking that mass away. But that's not true, right? So, since we say that it's equal mass and radius, we are taking all that mass and we are just pushing it to the radius. So now the radius of the sphere has all of the mass. So when you think of moment of inertia, right? Moment of inertia being the summation of all particles and their radii squared, all of the particles have the same mass, but now they all have the maximum radius possible. Whereas in the solid object, they start at the center of mass and they slowly get bigger and bigger. Whereas with the shell, it's just already at the full maximum value. So that is why there is this common discrepancy between solid and shell moment of inertias. All right, that's going to do it for our video on calculus moment of inertia, and we'll continue on to use something called the parallel axis theorem in the next video.